Hello again, and this is ME4111. We're on tutorial sheet 5, and we're looking at question 2. So again, this is on free body diagrams. So we're asked to correct the wrong or incomplete free body diagram for the scenario that we're shown. So we're given this lawn roller of mass M being pushed up an incline, which is an angle of theta. We'll see the effort at the free body diagram here. So again, with the object drawn in isolation, that's fine. We have a normal contact here. Instead of the plane, we just have the normal contact force. That looks good. We have the force P being transmitted by this connection here. Again, that's fine. That's been shown. And then when we look at it, we see that the weight is being indicated acting down the plane, which isn't true. Okay, so the correct way that should be pointing is to come down like this. Okay, so we'd have mg acting down and just scribble it out there. All right, so that would complete that free body diagram there. The second one then we're asked is this Prybar lifting the body A, which has a smooth horizontal surface. So this surface here is smooth. So that means we just have a wall normal reaction force. And the bar rests on horizontal rough surface. So this surface here is rough. U-G-H, and this one here is smooth. I should use a different color for it, but sure. Very hard to write with a mouse. Okay, so looking at our free body diagram, we have the object in isolation. That's great. We have the load transferred from this object A, this body. So that's great. That's in. We have the force P, which has been applied here. That's fine. And we have the normal reaction force here, which to me seems to be pointing in the wrong direction, but you could leave it that way and you get a negative in your answer, which is fine. But because the surface is rough, it will also support a friction force. Okay, so we would have our lateral reaction component there, which we'll call F. And in essence, in terms of equilibrium, if we decompose this force here into its two components, you would have this and this. So we'd replace that with that. And this force F will be balancing out that component there because these ones are vertical. And this one, you can see, because this is pointing down, this component is pointing down, this one's going to be pointing up. Okay, but again, you could leave it in. You'd have minus R minus N minus P cosine of that angle equals 0. So you get a negative for N, which is telling you that, in fact, it's pointing the opposite direction. Okay, so that's straightforward enough. The next one, uniform pole of mass M. So the weight of this is important. In a position by a winch, supported with a notch to prevent slipping of the pole. Okay, so that notch will allow rotation and it will prevent movement in the plane, through the plane, and also in the lateral direction. So look at my free body diagram. I've got my object in isolation. Instead of the cable, I have the tension T, so that's good. I have the weight of it, Ng, acting at the center of gravity. That's great. Yeah. And when I come down here, I can see I've got a wall normal reaction force, which is fine. But I'm missing one in this direction here. Now, if I look at the figures, this one will have a horizontal component, that is a vertical. So in fact, it's going that way. But again, I could have left it the way I drew it originally, and I get a negative for my answer, which tells me I had it pointed the wrong way on the in the free body diagram. Again, just remember that just because if you get a negative on it doesn't mean that it's in the negative direction. It means that it's the wrong way in your free body diagram. So if I had minus, if I drew it like this, although my force is pointing here, shown in the negative direction, the minus on it means that it's just pointing the wrong way. It's actually a positive force. Okay, so just be aware of that distinction. Now we've got a supporting angle bracket for a frame of pin joints. So all these things are pin joints. Okay, so again, we've got a load on this here. And you see that this is where students would often go wrong, is they draw the whole thing. And what you're really interested in is just this bracket here. Okay, so again, this bracket is drawn in isolation. We have a load transferred to it from this member, which is going that direction. That's fine. We have a reaction force down here, just shown pointing down that way. We're not told anything about the mass is, so maybe the mass is important. I think we're told to neglect it unless we're told, so we're not told, so we'll neglect it. This is a pin joint. So again, it can support a vertical, a horizontal component, like so. And likewise up here, we could equally have one there. They will not support any moments. Again, don't be distracted by the stiffness of this structure. Look at each joint in isolation, so make it cut and decide, well, okay, if this is cut here and I try to rotate here, would it allow it? And it certainly would. Again, if this is cut here and I try to rotate above B, this bit here, it certainly would be allowed to rotate above B, so I'd have no moment reactions there. All right, next question. Is this the last one? It is. Great stuff. A bent rod welded to support at a subjected to 2 forces in the couple, or 2 forces couple, right? Coordinate system. As welded in, so it's a fixed support. Right, so we have object in isolation. I got my couple applied. I have the force P. I have the force F. Right there on. I have one reaction force in there. I would have a second one in the x direction, so AX. And because this is a built-in support, now if I have this cut and I try to rotate either way against this, about this point, it would react to it. It would try and stop it. So I would expect a moment reaction. Again, I could assign the direction arbitrarily, but taking a look at the forces, this is going to swing it clockwise. This one swings it clockwise. This one swings it clockwise. So chances are it's going anti-clockwise. So my reaction force would be in that direction. Sorry, not my reaction force, my reaction moment. Okay, so again, I can write that in A. Okay, so that concludes that. So again, the process for all these is just to look at the system isolation, say, right, if there's a cut there, and I try to push it in the y direction, push it up or down, pull it in or out of the wall, will there be a reaction force? Will it try and stop that? If I try and rotate in a clockwise or anti-clockwise direction, will it allow that moment? And that will tell me what's going on. If in doubt, you can just refer to tables, and there's a set of tables given in the book that indicate what reaction forces are appropriate. Okay, so you should be pretty comfortable with that. They're all pretty straightforward, nothing too tricky there. And just get comfortable with those. And just remember that for all your equilibrium problems, you draw a free body diagram. And in the exam, there's a chunk of marks going for doing good free body diagrams. They don't need to be a work of art. They just need to be the object in isolation. So there's no surface shown here or any of that nonsense. There's no cables connected onto it or anything like that. Just the object in isolation. And instead of contact, you show the forces. And again, just indicate your coordinate system. That is always good practice. Okay. Okay. We'll drive on with the next couple of questions.